So hello, everybody. I'm Terry. I'm with the Montana Watershed Coordination Council, and the presentation today is all by um, Adam Sigler with MSU Extension and Abby Ebert with Montana DEQ, Water Quality 101, key concept for surface water monitoring, which you can all see. And MWCC is just hosting this. This is also in partnership with Monitoring Montana Waters and Rachel Mallison. And just to let you all know, Adam and Abby are going to give a presentation, and then we're going to have time at the end for Q&A. So as you're listening, if you have kind of a clarifying question about what they're talking about, feel free to drop that in the chat, or a question you just don't want to forget, put that in there. But we will respond to, or they will respond to, more substantive questions after the presentation, just to keep things going. As hopefully you noticed, this is being recorded, so we will share out this recording as well as the slides with everybody who registered, so you can catch those things later. And during this next hour and a half, if you have any technical difficulties chatting or hearing or whatever, just message me directly and I can take care of that for you. But other than that, yeah, we'll just get started. So thanks again to Adam from MSU Extension and to Abby from DEQ for, yeah, giving this webinar for everybody, and take it away.
Great, thank you, Terry. Yeah, so I am, in addition to being the water quality specialist with MSU Extension and an assistant professor here, I'm the chair of the MWCC's water committee, and Abby is the co-chair. So we're excited to be able to represent both our own organizations and be representing also Montana Watershed Coordination Council. And so I am here in Bozeman working for the public education branch of the university. So I have responsibilities across, the biggest part of my job is outreach and public engagement, but I also do research and I do teach as well. And Abby, do you want to take just 1 second to introduce yourself here?
Yeah. Hi, I'm Abby Ebert. I am a senior water quality monitoring scientist with Montana Department of Environmental Quality. I work in our monitoring and assessment section, doing water quality monitoring and analysis for our integrated report, which a part of that is our impaired waters list. So we monitor a variety of parameters throughout Montana.
So thanks, Abby. And so where we're headed with the talk is a little bit of background on watersheds, law and policy, some of the common analytes and monitoring for those, what are some of the important controls on water quality and addressing pollution, and then a little bit about sample analysis plans and some resources. So both Abby and I, as well as Rachel Mallison, provide a lot of support to stream teams monitoring across Montana and bring in some of that context as we go here. But Montana is very much a headwaters state, and we send water to 3 different oceans from Montana. So there are millions of downstream users that are using water that has a quality that we help determine by what we send out of our state. And not only the natural geology of the landscape and vegetation, but the land use on the landscape helps to determine water quality. And you can see here 2 very visually different water qualities in these 2 streams mixing. And this is a picture of a water drop that I took sitting on a field form at one point. And I like to use pictures of water drops to think about the fact that I think that water has a memory, is a way I like to describe it. If we can interrogate that drop of water, we can look at the chemical, physical, and biological memory in that drop of water that will tell us about the path it took to where we find it. And so even if we use our most advanced analytical methods to test this drop of water, we could find non-detectable, like nitrate, let's say. And so we can't find any nitrate in there with our most advanced instruments. There could still be billions of molecules of nitrate in that drop of water. Because if you think about Avogadro's number, it's 10 to the 23rd molecules per mole of a substance. That's a huge number. So it's just to say that there is this chemical memory that water carries with it along its path, moving through our watersheds. And Montana being a headwaters state, this image just shows smaller streams coming together to form larger streams. And more than 80% of the stream length on the planet is first order streams, or those smallest streams. And that's really important because that is where the water quality trajectory is set for our bigger rivers. And if you think about this, when we're in these small streams where we've got a lot of land use relative to the amount of water there, we can really influence the water quality in that stream compared to a river the size of the Mississippi, for example, where now if you think about that same land use sitting on the bank of this small stream versus sitting on the bank of the river, it's a lot harder to influence the water quality once you get into these large rivers. So again, very important to think about water quality management in headwater streams, even on the smallest streams that sometimes we might want to overlook. So if we think about water quality in the landscape context and we observe a water quality issue in a stream, I want to just pose this question now, and then we're going to give a lot more context for this over the course of the webinar. What do we need to know to make management decisions to address this water quality issue? So we've got this landscape spread out above us. What do we need to know about this water quality issue to address that? So water quality management in the United States has a long history. An important part of that is the Cuyahoga River in Cleveland, made famous by a Time magazine article in 1969 as the river that oozes rather than flows. And so due to mill waste on the surface of the river catching fire and not being able to be put out, this caught the national attention like nothing had before, and really helped to catalyze a lot of change, including the passage of the Clean Water Act in 1972, which sought to make the nation's waters fishable and swimmable. And there was the Safe Drinking Water Act, which also helps us to manage our water quality in the US. The formation of the Environmental Protection Agency also happened at the same time. So one of the provisions of the Clean Water Act is to understand which waters are of high quality, but how do we define that? And so if I ask you, if you're going to drink some water, then how would you think about what determines whether that's high quality water or not? And in contrast, what if you're going to use that water to wash your car? Which of these different types of water would you say has the highest quality for those two different uses? And the point here is that water quality is a subjective term, that it depends on what the beneficial use is. If I am drinking this water, then I personally probably care the most that it's disinfected so that I'm not going to get sick from microbes in that water. But if I'm washing my car, I might care most that it has a low level of calcium and magnesium or hardness that's going to leave spots on that car. And so to bring it into more context of actual streams, these are the things that Montana has determined we want to use our water for. And it's pretty all-inclusive. One thing I'll point out is that we have both cold and warm water fisheries on there. And so that is a nod to the fact that those two things can't happen in the same place at the same time, where there could be a little overlap, but basically those are different waters. And this highlights the fact that Montana is very different from the West, where we have these relatively cold, low salt, fresh mountain streams, to the east part of the state, where we have these prairie streams that are naturally a lot higher in sediment and salt and are warmer. And so if we're going to determine what is high quality water for these designated uses, we need to account for this natural variability. And so in order to do that, we start with standards. And all water quality standards are start with a narrative standard. And this is an example of the standard for sediment, where we can't have increases above what's naturally occurring that causes nuisance or injury to the different beneficial uses, right? So each of those parts I just talked about are wrapped into this narrative standard. And whenever possible, we also want to have numeric standards, because that narrative has different people could interpret it differently, and it could be a bit subjective. So we want to, wherever possible, apply numeric standards so that there's a threshold and we know that below this threshold, things are okay, and above it, we might see problems. So once we get to that place of having set numeric standards, which Montana Department of Environmental Quality has done, we're able to go out and start assessing the waters of the state. And Montana DEQ has broken the state's 60,000 miles of perennial streams and rivers up into about 1,000 assessment units, and have identified that almost half of those are impaired for one thing or another. And you can see here that sediment is at the top of the list for causes of impairment. We also see on here a couple of different sources of nutrients, types of nutrients, nitrogen and phosphorus, and then also a number of metals, which are a nod to Montana's mining legacy. If we look at the sources of those impairments, we see a number of things here that are the main causes that impair the most stream miles. And there are some land uses on here that just cover a large fraction of the state. So there are some agricultural land uses on here. There's some roads on here, things like that. One thing that is notably absent from this list are any point sources. These are all non-point sources of pollution that are the top contributors to our water quality issues in Montana, and that's true nationally as well. So point versus non-point, this is a critical issue. That some of those most egregious issues back in the 60s and 70s were from point sources of pollution. And classically, these are things that dump into a river out of a pipe. And a wastewater treatment plant might be a good example. In many respects, these are relatively easy to quantify, at least, and to address, because you could go test the quality of that water coming out of the pipe. You could see how much flow there is, so you know how much pollutant is being discharged. You follow it back up to the source, and there's an entity there typically that can be held responsible. This is in contrast to non-point source pollution, which comes in spread out across the landscape. All of us contribute to non-point source pollution where we live and work, and it's spread out over space. It also comes in underground, sometimes through groundwater or during storm events. So it's a lot harder to quantify, and we're all responsible for this. So it's a lot more complex. And these two types of pollution are dealt with in very different ways under the Clean Water Act. Point sources are dealt with under a discharge elimination system, whereas non-point sources are dealt with under the Section 319, the non-point source section. And the critical distinction is that point sources are under a permit system and non-point sources are dealt with under a voluntary framework. And so that means that the majority of our water quality issues that are caused by non-point sources of pollution have to be dealt with because people want to deal with them. And that's a big part of what I do in my work, is trying to help people understand what the issues are and what they can do. So the Montana Department of Environmental Quality is the primary agency in the state working on water quality. And if you go to their website and click on water up here and go to resources, then you can get to a search for water quality assessment information and get to a map that is created every couple of years. You can click on the streams and it will pull up different information about what's known about those streams. I've clicked on one here in the Gallatin Valley, Camp Creek, because it has a number of things listed as an example. So it will tell you, you can learn about the fact that it's listed as impaired for nitrogen and what some of the probable sources are, and so on. A lot of information about what the water quality issues are there. When a stream is listed as impaired, meaning that its water quality is not good enough to meet the beneficial uses, then it's on the 303D list as impaired, and a total maximum daily load will be written for that. And so this is an example from the East Gallatin, or the Lower Gallatin. And to think about what a TMDL is, this is a really helpful planning document. We've got our stream here. If we think about sediment, we've got these different sources. Let's say we've got some eroding roads, we've got some eroding banks, we've got stormwater runoff, and we've got a wastewater treatment plant. A total maximum daily load is going to assign numbers to those. So let's say we've got 100 kilograms per year coming off the roads, 300 from banks, 100 from stormwater runoff, and 50 from wastewater treatment plants. This TMDL puts all of those numbers in the same units, which are going to be measured in really different ways. We go to that pipe and measure how much sediment concentration is there for the wastewater treatment plant. That's relatively simple. Stormwater is going to be measured probably in pipes, but that's coming off only during storms. So when did that storm happen? Were you able to get out there and sample it? How are we going to quantify how much sediment's coming off a bank like this? It's going to be perhaps the height of the bank and the length. So, and it's only going to happen during high flow probably, and then forest roads also. So all of these different things, a TMDL is working to account for these sources, also natural background. And then what is our current load, and how much can our stream handle without being impaired, and how much do we need to reduce? So this concept of comparing apples to apples, we want to know which are the most important sources, because if we need to know we need to drop this sediment load by 200, and the only place we can deal with it with a permit is at the wastewater treatment plant, we can't get there because they're only discharging 50. And it's probably going to cost millions of dollars to make that improvement, while meanwhile upstream we've got these other areas contributing from eroding banks or forest roads, potentially much more cost effective to address those. And so figuring out how to get the biggest bang for your buck on putting management in place is something where we get really useful insights from a TMDL. So thinking about, again, for an example, the East Gallatin River for total nitrogen now, if we go to these pie charts are the kind of concept you can expect in a TMDL. And so in this case, we know that we've got about a fifth of it, this nitrogen coming in is from background, about 2/3 from agriculture, and then a couple of other smaller sources. This is well upstream from Bozeman. If we move down into Bozeman, then how do you think that pie chart is going to change? We've moved downstream, and now we're capturing a bigger part of the landscape. Residential development is now about 1/3 of the total nitrogen contribution from to Bozeman Creek. If we go down a little bit further, down well below Bozeman, how do you think that pie chart will change now? When we flush our toilets here in Bozeman, it goes to the water reclamation facility and is treated with a $50 million treatment facility. And still, even with that very advanced treatment, 40% of the total nitrogen entering the East Gallatin is from the wastewater reclamation facility. If we go a little further downstream, then we do bring in a lot more of the west part of the valley here, and now agriculture bumps back up. But so this concept of where on the stream are you, and what is the land area above you, and what are the most important contributions, again, is something you can hope to glean from a TMDL. So water quality can be thought of perhaps in at least these three big categories. So physical is going to be everything from sediment, and even we might include channel form in there, the shape of the channel. You might put temperature in that category. Chemical might be anything on the periodic table, or more emerging personal care products or pharmaceuticals, anything basically that's chemically dissolved in the water. And then under biological, we've got macroinvertebrates that sometimes get monitored for water quality, that are the base of the food chain, critically important. We've also got what we might call the bad bugs like Giardia or waterborne pathogens that are also biological and in the water that could be monitored too. So we're going to walk through just a couple of these different parameters, what they are and why we care about them, and then how they're monitored in a pretty simple sense. So sediment, we can see two very visibly different sediment concentrations in these two streams. And so in the simple context, this suspended sediment is you dip a bottle in and then how much sediment is in there. Sediment transport in streams is very natural. We often have this very sinuous shape where streams are bouncing back and forth off their edges. And for anybody who's ever camped on a desert river, this point is really important because the sandbars on desert rivers are the places where you camp. They're the nice places where there's a flat deposited area, and all of that point bar formation and erosion is a natural process in those desert rivers. And if you go camp on a desert river downstream from a dam, then you'll notice a big absence of those sandbars because all the sediment has been trapped behind the dam, and that causes a variety of problems. And so this is just to say that streams moving back and forth and causing erosion on their banks and constantly moving around and creating this mosaic of different land ages in the riparian corridor is a very natural process. When sediment loss gets out of whack, this is an example of an agricultural field that has high rates of soil loss. That's a problem because soil takes thousands of years to form. So it's creating issues with our ability to grow food and crops on that landscape. And then once the sediment gets into the stream, it can silt over the gravels for salmonids that want to spawn and smother their eggs. It can also smother the gravels that macroinvertebrates, those bugs in the stream, need to take refuge from flows. And so a lot of issues, not only from where it's lost on the landscape to where it ends up in the stream, can cause problems with sediment. So a classic way to monitor sediment is with grab samples. You go collect that sample, you pour it through a filter, you weigh how much sediment is left and on the filter, and then you divide that by the volume of water and you get a concentration. Turbidity is related to sediment. So in a lake, you might dip a Secchi disc down into the water until it just disappears. And that's the Secchi depth or the clarity of the lake. And sometimes in streams, we have these simplified transparency tubes that basically is lowering that same Secchi pattern disc down into this tube of water that was just filled out of the stream. And so a semi-quantitative way to do really easy turbidity measuring in a stream. A more precise way to measure turbidity in a stream is with a turbidity meter, where you take a sample, put it into the sensor, and the sensor shines light at it and sees how much is deflected off. And that's reported commonly in NTUs or nephelometric turbidity units. So these are all things in the water column, but a lot of measurements now are made on the channel substrate itself. And so this is not thinking so much about what's in the water column, but what's deposited on the bottom, as we could see through this polarized lens here. And so we might do that with pebble counts, measuring the size of the rocks at different places in ripples, which we could also do with a gravelometer, where a rock passes through different size of holes, and then depending on which one it doesn't fit through and does fit through, that gives you a bracket of the size. And then you can quantify all the way down to very fine sediment, that's typically more common in riffles or fast water habitats. Another way to look at channel substrate is with pool tail fines. And so this is, these substrate measurements are a way to get at what's happening over a longer period of time. While that grab sample was just what happened at that very instant that you were there collecting the sample, these substrate methods are more of a time integrated. They're how much of that sediment was settling out in this pool, for example. So pools are slower water habitats. Water comes in and slows down and sediment might settle out. And so by putting a grid out on the tail of the pool, we can see what fraction of that pool tail is covered with fines, for example. And that not only is a method to see how much sediment has fallen out in that stream, but also it's directly related to those fish that wanted to spawn in those tails of pools in many cases. So again, a lot of fine sediment can smother those spawning gravels and not allow those fish eggs to emerge and survive. So those are a couple of different ways to quantify sediment. Nutrients. So why do we care about nutrients? We put nutrients on our lawns in order to make them really green. We similarly add them to our agricultural fields to be able to feed our global population. And nitrogen, phosphorus, and potassium are the three numbers you typically see on a fertilizer bag. And nitrogen and phosphorus are the two most commonly limiting nutrients, and the nutrients that plants can't get either from the water or the atmosphere. For the same reason that adding nitrogen and phosphorus to our lawns and our crops increases their greenness and productivity, streams will also turn green when they get nitrogen and phosphorus in them, because that nitrogen and phosphorus are the two nutrients most commonly limiting of this algae growth in streams. And so this is an issue not only in streams, but in reservoirs, and can have a lot of impacts for economics and for recreation. Eutrophication is the process of a stream becoming really fertile like this, and a lot of growth happening. And something that happens behind the scenes here that you can't see explicitly is these big daily changes in dissolved oxygen. So we think of with eutrophication, the issue being low dissolved oxygen, but it's also important to realize that it's not just low dissolved oxygen, it's also very high during the day when all these plants are photosynthesizing. So we get really high photosynthesis in the day and really high dissolved oxygen. Then at night, the sun goes down, photosynthesis stops, and the DO in that water just crashes. So right at about 6 a.m. before the sun comes up is where you've got the really low dissolved oxygen. And that's when a lot of aquatic life is really struggling to survive in these eutrophic systems. So there, I'm going to actually, the last slide here before transitioning over to Abby for a minute is monitoring for nutrients. And so this is a video that we have on our website about how to collect samples. Nutrients are typically grab samples that are sent to a lab. And so you go out and get bottles from a contracted lab, fill the bottle out in the stream. Here, we're using preservatives, nitric acid and sulfuric acid to preserve these different samples. You can also preserve samples by filtering them. So this is a capsule filter. You fill the syringe, add a filter, and then squeeze the water into a sample bottle and filter out the biology that might cause problems with converting the nutrients in that sample, for example. But preserving the samples and then taking quality control samples. So this is collection of a blank that's happening here, so that you know that when the samples get to the lab and filling it, you've filled out the paperwork, you have put the chain of custody in the box, in the cooler, and mailed it to the lab. You're by collecting blanks and duplicate samples, then you can have confidence about the quality of the data that you get back from the lab. And so the workflow for getting nutrient data is pretty different from that sediment workflow we just looked at, where a lot of observations are made in the field, because you collect the bottles, you send them off, and then you end up with a spreadsheet back from the lab. So with that, I will turn it over to Abby to talk about chlorophyll.
All right. So Adam did a really good job explaining how nutrients impact chlorophyll growth or overall algae growth. I shouldn't say chlorophyll growth, but chlorophyll is the pigment that algae produce, and is it that bright? It provides that bright, vibrant green color. So we see algae growth kind of two primary ways in our streams in the state of Montana. The first way that you see on this picture here is through microalgae growing on the substrate, whether that's rocks or on top of the muck or sand or silt. And right now that algae is kind of building up and decaying, and that's why it's kind of that brown color, but it's still producing or causing some potential impacts to the environment. Next picture, Adam. Another type of algae that we see in Montana is filamentous algae, another type of green algae. You can kind of see in the hand that dark green color. That's kind of an indication that the filamentous algae is mature. But as maybe you can kind of see in the water, kind of underneath the hand, there's long strands of that filamentous algae growing that's more brown in color. So it's decaying, and that can also cause larger fluxes in DO2 as we have more decomposition of those large algae mats. Next picture. Click one more time. So when it comes to algae growth and in relation to chlorophyll A, we think about the primary beneficial uses that undesirable algae growth can impact. And the first one is recreation. So next picture, Adam. So this picture is an example of some excess or undesirable algae growth occurring on the Smith River. We had a research project recently there the last couple of years. And so we see excess algae growth occurring, and how that can impact recreation is, for one, our standards and modeling section did a project with the University of Montana and Dr. Vicki Watson on kind of how green is too green. So how much algae growth inhibits the desire of recreationalists to want to be in rivers. So just looking at water quality potential impacts might sway someone from wanting to recreate in a certain body of water, but that also can also impact fishing by snagging lures or flies a little bit more often too. So it's kind of two ways that it could impact recreation here in our state. Next picture, Adam. The next main reason why we monitor chlorophyll A is our aquatic life. So Adam did a good job of already explaining the fluctuations in DO. So if he clicks next. But another big shift on excess algal growth, or that kind of undesirable filamentous algae, or even really thick mats of microalgae, that can impact our aquatic invertebrates as well. And so that top macroinvertebrate that you see is a nice golden stonefly. Those like very clean, cool water. They're intolerant to pollution, but also large fluctuations in dissolved oxygen. They like cold water that's nicely oxygenated. And so when we have these big algal mats causing those fluxes and kind of messing potentially with their food sources and overall substrate, we can get a shift in the macroinvertebrate community to some of our more tolerant macroinvertebrates, because all macroinvertebrates are important for the overall ecosystem. So they are present no matter what, but they start to dominate the system. And so that's the example of the bottom picture of our midges. So those are our fly larvae before they emerge out of the water. And that can also impact our fisheries. Trout have preferences on eating, and some macroinvertebrates, based on where they live or what food sources they go after, can also impact the feeding and responses to trout as well, because you might see a shift in the hatches as well that trout typically can rely on for good food sources. Next picture, Adam. And one more, sorry. Another important aspect, like Adam was describing with DO, this is just kind of like a long-term aspect of DO fluctuations with temperature. We get those daily temperature fluxes on top of the daily DO fluxes, and that can really stress out macroinvertebrates and fish and cause them to move, or can cause, sometimes depending if they can't move, potential fish kills. And we see this not only in our river systems, but we can also see it in our lake systems as well, especially in the wintertime. Hyper-eutrophic to eutrophic lakes that are eutrophic because of man-made sources of excess nitrogen can have these big fluctuations, and that's when we see larger fish kills when ice comes off. And it's because of all that decomposition of the algae that was growing over the summertime, really taking up all that oxygen that it could that was normally available throughout the whole winter. Next kind of couple clicks, Adam. And then I just want to highlight that agriculture can also be impacted. The two beneficial uses that are the most sensitive are aquatic life and recreation. But when we have excess nutrients, and a lot of our state agriculture is supported by irrigation ditches, and so when we have a lot of excess nutrients and warm waters, that can help Cladophora, that's filamentous green algae, to thrive in also our ditches, which can plug them up and be quite a bit of a hassle as well to our irrigation infrastructure. So it also can impact the, the agricultural beneficial use as well. Next, Adam. Oh, that's weird. Okay, there was some, oh yeah, okay. So go one click back, if possible. Okay, so when it comes to methods, there's kind of two ways to potentially think about this. The first way is a little bit easier for some of the volunteer monitoring groups to participate in, which is our aquatic plant visual assessments. So that's kind of documenting the overall growth of algae, macrophytes, microalgae, and moss, aquatic moss, in our streams. And so with that, you can document the percent growth within the wadable zone of a stream. So that's anywhere about a meter or so deep that you can safely wade, and you can also see the bottom. This only works on streams and rivers in the state that aren't too turbid. If you can't see the bottom, you can't quite do this method. But it really only requires some human eyes and the ability to take notes on a piece of paper and have that piece of paper. So there's a couple groups that do this, documenting at the sites that they collect water quality on, and that helps them kind of look at seasonal trends at their individual sites. They kind of see when algae is growing during the year and how bad it could potentially get. As we click on the next image, the second option that people can use to monitor algae is a little bit more intensive, and that because it requires you to take actual algae samples. And so the first part of that is setting up your overall reach length. And so you have to determine that by getting wetted with measurements across your stream and taking that average wetted width and multiplying that by 40. If you have a smaller stream, you need to have at least a reach or a total site length of 150 meters. So sometimes those total site lengths can get quite long. But once you have that total site length, you can divide that by 10 so that you can flag 11 transects, A through K, and that's what you see on the diagram here. We have that meandering stream with those 11 transects equally spaced apart, A through K. Next, Adam. And so when you get to those individual transects, you're going to move in some sort of right, left, center pattern. And the reason you do that is you want to decrease bias as much as possible when sampling for algae. And so not only are you not selecting your transects on where you sample, so you get a variety of habitat, but you're also not going to pick up or take your sample in the heaviest growth area all the time, because if that's not what your site kind of is telling you to do, then you don't do that. So when you have to decide, let's say you're at transect A, next, Adam, you see that The substrate type is kind of mucky, and it has microalgae growing on the top of the muck. And so, as you can see, Katie is holding a core, which is just a syringe with the syringe top cut off of it. And what you're doing is you're just coring out that little bit of algae that's growing on top of the muck, taking a sample of that, putting it in a centrifuge tube, labeling it, wrapping it up in tinfoil, putting it on ice so that you can ship it to the lab. Let's say now that we're moving to transect B next, and you notice that the substrate type is predominantly like a cobble gravel bottom, and it has primarily filamentous algae growth growing. And it was hard to find a good picture, so I just used from our training. So imagine Katie is in a stream and not on a nice lawn of grass, and she has a hoop that's already a designated circumference and is collecting all that algae within that hoop and putting it in a bag and sending it off to the lab. The next method you can potentially use is, let's say we're at transect D now, and our substrate type is predominantly a cobble gravel bottom, and microalgae is the dominant algae that's growing. We do a template method. So we pick up a random rock, being unbiased, not looking at where we're gonna go grab in the stream, and you put that little piece of PVC pipe that's cut and put that also randomly in a spot on the rock as well. And now you're going to scrape all the algae with either a toothbrush or pocket knives or whatever you can do to get that algae off. So next picture, Adam. So as you can see in the picture, Katie is scrubbing that rock with a toothbrush. Next. And we want to make sure that we collect all that algae within that area of the PVC pipe, and we collect that next in a filter apparatus onto a piece of filter paper and collect all that algae that we scraped off on that rock that can be sent to the lab. Next slide, please, Adam.
Thanks, Abby. And I just want to make sure that we're checked in on time. I think we probably need to move a little quick to get through all our slides here.
Sounds good. Thank you. Next ones are quick. That one's the longest. All right, now moving on to metals. So like Adam said earlier in the presentation, Montana has a rich history of mining in our state. And so our Montana DEQ standards program has developed standards for metals in our state under DEQ 7, and we have standards for not only human health and drinking water, but we also have standards for aquatic life. For aquatic life, we can see standards for chronic exposure, so that means a long-term duration at a short concentration, or we can have acute standards, which are short-term exposure at a high concentration. And so our main sources of metals are historic mining or even some current mining operations, but we also can see metals come from our natural landscape that is amplified with human activity. So if we have a lack of riparian habitat and we increase erosion, that sediment that's naturally found in our soils can end up in our waterways. And also, we also have a lot of natural background because we are a rich metal state. Sometimes it just can come from the natural geology as well. And a good example of that is arsenic on the Yellowstone. Next, Adam. With metals sampling, it's very, very similar to nutrients. We're just collecting either grab samples when you collect total recoverable metals, or you can collect filtered samples for dissolved metals. An example of a metals that you would want to collect to filter for dissolved is aluminum, because our aluminum standard is based on the dissolved aluminum fraction. And then the last method that you can consider is sediment metals. Sometimes it's good for source assessment if that's a goal of your project, to kind of get at what is in depositional zones of your stream sediment for metals concentrations. Next, Adam. And then the last parameter that I will cover, and then Adam will finish off, is E. coli. So E. coli is a type of, or is a subgroup of total coliform bacteria, which comes primarily from feces of warm-blooded animals. And E. coli are a large, diverse group of bacteria, but not all E. coli cause illness, but they are a great fecal indicator bacteria for state surface waters. And so our primary sources of E. coli in the state of Montana can be livestock, but also can be just our overall impact with our own potential fecal contamination through point sources or septics, kind of depending on where you are at in the state. Next slide, Adam. And the E. coli methods can be pretty simple, or they can take some time if you're going to process them in-house. So it's really important when you're monitoring E. coli that you just are aware and you read standard operating procedures, because E. coli can be impacted by weather, light, and other factors pretty easily. We expect to find E. coli after rain events, but you don't always want to bias your samples. And so, but overall, with collecting E. coli, you collect it just a simple grab sample, but it has a really short hold time. The current hold time for E. coli is 6 hours. And so you either have to make a choice to quick drive to the lab and drop them off, or you kind of see the pictures here of how some of the machinery or steps to analyze and prepare your own E. coli samples. And so with that, I will pass it off back to Adam.
Awesome. Thank you, Abby. Yeah, a couple more parameters here we'll highlight and then move on to some bigger picture concepts. So field parameters are the things that you don't measure in a bottle. And so these are the 4 most common field parameters, things that you measure with the meter in the field. And that's because these things, at least the first 3, will start to change as soon as you take a bottle out of the stream. And so temperature we'll talk a little bit more about in a second. pH, the acidity or the concentration of hydrogen ions in solution, which controls a lot of things like metal solubility, dissolved oxygen that Abby just talked about a lot that the bugs need and the fish need, and then specific conductivity I'll touch on a little bit more too. So different field meters that you take out. We have a video on our website about how to calibrate field meters. And basically there are these different probes on here that this is a pH bulb, this is a DO sensor, and this measures specific conductance and temperature here. Another probe we were working with for a little while. A key thing about field parameters is that you have to calibrate, right? So this is a known pH. You put your meter in there and you tell it that that's pH 7, put it in here, tell it that's 10, and so on. And that is critical to getting good quality of data. So specific conductance, this is an interesting one I just want to touch on. And for a funny kind of way to remember this is that if you are taking a bath in a bathtub and you've got a radio perched precariously above you on a shelf, do you want to be bathing in seawater or distilled water? And probably a lot of people said distilled water, and that's because it's the salts that are dissolved in the water that conduct electricity. And so we have this really nice relationship between how much electricity water will conduct and the total dissolved salts in the water. So that specific conductance is just a way of estimating the total ions in the water pretty accurately, and that's a field parameter. pH, I just want to bring up a couple of challenges. This is based on some work that we've done with some groups where we were comparing across different meters. This is a long-term data set with pH, which could be really exciting to be able to analyze. But then you start looking at the data and you see these big excursions down to 6 or even 4. And it's like, wow, was there a crazy water quality issue in that watershed? No, it actually probably was a probe issue. These vertical lines here are probe replacements, and obviously these points here were really high right before probe replacement, which is what prompted probe replacement. Another watershed group had a similar issue where you get these crazy excursions. And basically, the point here is that you really need to do a good job with your calibration logs if you want to have robust pH data. Specifically, I think it's really useful to have these times in your calibration log that I put the meter in pH 7 at this time and it read this, and then this many minutes later it read this. This basically lets you see how long it took that pH probe to equilibrate, which is a really good indicator of whether it's about to go bad or it's going bad. So if we had this level of detail, we could go back and sleuth through all this data and find out what data is good and bad. But as it is, actually, we're not using any of this data because we don't have confidence in it. And so it's unfortunate. This is like approaching a 20-year data set, but because there wasn't as good of records as we need, we can't really use the data. So pH is particularly problematic because those probes only last a couple of years. Diel variation. So this is something to be very aware of with field parameters. Getting all of those field parameter numbers are really useful context for other samples, but you should be aware that these parameters, like temperature, swings every day. This is like 10 degrees Celsius that this stream temperature is changing. And temperature I put up first because that's perhaps the most obvious one. This gray here is daily air temperature. And so it's very logical and easy to conceptualize that the water temperature is also swinging a lot on a daily basis. So if you're trying to characterize things that are happening with temperature, then going out and collecting a sample at whatever time of day you happen to be there is going to tell a very limited part of the story. The same is also true for dissolved oxygen, as we talked about before, right? So we expect, especially in the places where we're the most concerned about dissolved oxygen, that we're going to have huge daily swings. So this isn't to say you shouldn't collect field parameters, but you should be very aware of the limitations if you're monitoring for field parameters, because many of these things oscillate like this on a daily basis. Discharge. So we're most used to thinking about discharge as a hydrograph, right? You've got time on the x-axis and the amount of flow on the y. And it's just the volume of water passing a point at a given amount of time, and cubic feet per second are what we most commonly use. And discharge affects a lot of things, but just a simple illustration of why we need to have discharge as watershed managers is because let's say I tell you there's a stream with a concentration of 1,000 milligrams per liter and another with 10. Which one of those is most important if I have a limited budget to go deal with sediment? Well, the answer is you can't know without knowing what the discharge is. If the stream that's got the really high concentration only has a really low flow, this other stream with low concentration has an order of magnitude more load. And so even if I completely erase this one, it's going to have a pretty modest effect on the overall load. So it's just an illustration of why we need flow or discharge in addition to our chemistry data. And the methods, we've got a stream here, we string a tape across, and again, we just measure the amount of time, how much cubic water passes in a given amount of time. So we can measure width on the tape, depth on this top setting rod, and then velocity with a sensor. There's also a really simple way to get velocity by floating an orange or something. That's more of an estimation approach. Often we want to get a hydrograph though, where we've got hourly or at least daily data. That means we need to measure the water depth and deploy an instrument to do that, go out a number of times and measure flow, and then get the water depth at that same time, create a rating curve, and then use that equation to convert stage to flow. So that's just a really quick highlight of how you get a hydrograph. You actually put an instrument in to measure water depth over time, and then combine that with a bunch of manual measurements of flow like that. So a little bit about the big patterns that we see to kind of wrap things up here. In Montana, we have a snowmelt driven hydrograph, and so they typically look like this. If we think about sediment in the water, when is sediment concentration the highest? It's pretty intuitive. We've all seen this, that it's the sediment concentration is high at high flow. And so it might precede it a little bit because you could get this kind of landscape rinsing effect. but basically high flow means high sediment. What about salt? So sediment is the stuff that's suspended in the water. What about the stuff that's actually chemically dissolved in the water? It's not going to settle out. When do you think that is total dissolved solids like that are highest? It's in late summer or at base flow. And why is that? Because we are diluting the salts, is what some people will often say, and that's right. What are we diluting it with? Well, the closest thing we have to deionized water in nature is snow and rain. So when that snow melt is coming off, it's diluting the salt in the water. And so this is a really important concept for thinking about managing water quality, where if you've got water runs off over the surface when it rains, then it's going to contribute to this particulate or sediment. And if water infiltrates through the soil, then it takes a slow path, dissolving things that are in the soil, dissolving things in groundwater, and then emerging out into the stream during base flow. So if I tell you, you go out to the stream in September and you note that there's no snow left in the mountains and it's not raining, true or false, all streams are dry. False, right? Streams flow year round, and that's because the water is coming from groundwater. So out here in the fall, this is groundwater flow coming in, and it's got high salt because that water took a long path down through the soils and through the ground. So this concept of the timing of dissolved things moving into the stream and dominating versus particulate things is critical for understanding and managing water quality. And getting back to our question of what do we need to know to manage water quality issues that we observe in the stream. This is just an example of volunteer collected data that shows that inverse pattern. All of these rainbow colors are different sites on the Musselshell River, and the gray back here is flow. And we can see that we do, in fact, see this dilution in the Musselshell River when peak flow comes out of the mountains. And this is an interactive plot that you can see on our website, collected by the members of the Musselshell Watershed Coalition. Okay, so getting close to wrapping up here in our last few minutes. We've observed this water quality issue in the stream. What do we need to know? We need to know what the primary sources are on the landscape. Maybe it's a dog, but what if actually, in fact, it's the sneaky cats that we weren't seeing that were out there that were the source of this pollutant? We need to know what the primary sources are to manage this water quality issue. We also need to know what their spatial distribution is. Are they really close to the stream? Are they further away? How are these sources spread out across the watershed? What are the pathways the pollutant is taking? And this is critical, what we were just talking about. Is it overland flow or is it coming in subsurface? And what is the timing of that delivery? And so we got at this a little bit, that if it's overland flow, then it might be a fast response to precipitation. You could have particulate and dissolved things, and storm events are going to be a big driver. For these subsurface pathways, it's going to be a slower response. It's not going to be as directly responsive to precipitation. And it's only going to be dissolved things that move through the ground, not so much that particulate. And it's an important source at base flow are these contaminants. Thinking then about the driver is integrating all of these things together. How are these things, the sources, where they are, the pathways and the timing, how are those things interacting to result in this water quality issue? If we want to address water quality issues, we really need to think in this way. And so a couple of examples of overland flow, for example, this was a project I worked on where these animals were watering directly in the creek. NRCS funding helped the producer put in off-stream water and a fence back here, and then vegetation grew in, and there was effectively this vegetated buffer. We did this experiment beforehand where we simulated precipitation out here, and nitrogen and phosphorus were discharged into the stream from that precipitation. After the vegetation grew in, we repeated the same thing, and we got no response. And that's for a couple of reasons. Both the manure source had been isolated from the stream a little ways, and vegetation can be a really good filter. This is in contrast to this overland flow pathway to things that come through the surface. And so just quickly about nitrate leaching. If we've got water in the soil and this balance of water coming in and out, once the soil gets up to field capacity, it starts to drain out the bottom. When nitrate is there, that's present, that's really soluble. That's what we need to grow in our crops. And if nitrate is there, then when water's moving down, then we're going to get nitrate leaching. And so that way for contamination to move into groundwater it's a lost opportunity for agricultural producers, and it's an issue for downstream water. And it has everything to do with our soils and that, again, pathway of things moving through. So that's a groundwater source. And I also just want to highlight this other source that moves through groundwater are our septic systems, where we are purposefully discharging our wastewater into the ground. And this work in the Helena Valley shows an increase in nitrate concentrations in groundwater over time by Drake and Botter et al. And it's largely attributable to that recharge from septic. So to kind of wrap this up here, if we've got this story of a water quality issue, we need to understand these different parts. TMDLs can tell us a lot about what the most important sources are. We need to know where they are across the watershed. We need to think about whether they're coming off, things are coming off in overland flow or through groundwater. And if it's a surface water pathway, then we can address that with things like filter strips. If it's things through groundwater, then we have to think about management practices more in the upland and look away from the stream for those issues like septic system maintenance or hooking up to sewer. And then thinking about farm management practices for nitrogen use efficiency. So just wanted to give you a couple of these high-level conceptual tools. And I think being able to think about these things in terms of the driver is really important. So a few take-home points. We've got high quality water is a subjective term that you have to think about in the context of beneficial use. Non-point sources impair a lot more stream miles than point sources, and we need to engage the public in this because compliance is voluntary. While fish care about the concentrations of things in the water, as managers, we need to think about loads, which are concentrations times discharge. And then these points about where the sources, distribution, pathways, and timing, and how are they interacting is critical. We're a couple minutes after the hour, so I'm just gonna flash through some resources that we will make available to you all. We've got this volunteer monitoring catalog, and I think sample analysis plans are highlighted in there, very critical. We've got this method selection guide, MMSG document that's laid out. It's got a how to use, the different reasons people commonly collect data from source assessment and trend over time. All those kinds of monitoring reasons are laid out. Maybe you want to figure out current conditions. This guide will give you some thoughts about what to monitor for. We've also got a lot here on data analysis, and I'm just going to fly through this so that we can get to answering questions. We think about comparing data to thresholds in these documents. We've got video guidance on this. Load calculations, how important are these two different streams, and to contributing the total nitrogen load, for example, in Muddy Creek, and thinking about analyzing results over time. So we have all of these resources that we'll include in our follow-up message to you guys, and just want to end on this Montana Watershed Coordination Council's monitoring directory where you can go and see who's monitoring what where. And with that, I think we'll go to taking any questions.